All right. Guess what? I know that you guys been waiting for this very class all along. This is our last class of Survey of Physical Sciences. And, the idea of this class is essentially that we studied the universe, solar system, then we studied the rocks and the Earth's crust, then we studied the atmosphere. Now the last thing we have to study about this planet is the water bodies. So what we are gonna study today in this class is the waters that exist on Earth. Essentially, it's a very simple class. I don't think it's gonna take us a long time to go through these concepts. Very easy, very chill, and I am sure that you probably know most of the contents that I will be presenting here today because either you already took some class about it or we discussed this in previous chapters. Okay, so essentially we're gonna talk about the hydrologic cycle, which we already mentioned in the previous chapter, right? And also where this water can be found. And then towards the end, we're going to talk about the ocean, okay, and some of the ocean currents. Okay, so this slide is just showing you where the water on Earth can be found. Of all the chemical components, the water is the most abundant on Earth, even more abundant than oxygen, for instance, okay? Or even the mineral silicon that we discussed already, okay? So it's the most abundant chemical compound on Earth's surface. Water seen from the sky covers about 70% of all Earth's surface. And this water is 98% found in its liquid state and 2% is found in its solid state. And here I'm not differentiating between water that's, good for human consumption or not. I'm just talking about the states, all right? There is a very, very small fraction of that water that is also found as a water vapor in the atmosphere, okay? But we generally just separate 98 in liquid and 2% in solid, okay? Of all this water that's liquid, 97% is found in the ocean, and you can see here in this pie chart, is found in the ocean, and only about 3% of the water in its liquid state, or well, here I think I can divide the water between what is fit or unfit for human consumption. Let's make that division. So here, 97% of that water is in the ocean, so that's not actually fit for human consumption. We just because of the salinity of that water being way too high, and the rest, about 3%, is what we know as fresh water, which is the water that we can actually consume, okay, or that's fit for human consumption. But some of this water is not actually available. So about 2/3 of this water, that's fresh water, is found in the ice caps or locked up in ice. So water in solid states that we can't actually access because they are either in the poles or part of, for instance, Iceland, Greenland. So we can't actually access that water, and only 1/3 of that water is available for human consumption. Most of that water is found in sediments, specifically as groundwater. Some of the water is in the atmosphere, which will eventually precipitate, and we talked about clouds in the last chapter. And then we have about 1% of that water that's present in rivers, streams, or lakes. So the water that we actually use to take a shower, to drink, is in these 1/3 that's available for that's not in solid state. All right. We already discussed about the hydrologic cycle, which is how the water sort of cycles on this earth. Lots of that water, evaporates and forms clouds. Okay, most of the evaporated water comes from the oceans, but there are some evaporation that also happens from the water on land, like water from rivers and lakes. They account for 16% of all the water that evaporates, okay? But most of that is coming from the oceans. Then the water forms clouds when it reaches the dew point temperature, and then that moves to other locations, right? Those clouds can be transported to other locations. Then precipitation occurs, which is when the water returns back to the land. And then we talked about two types of precipitation processes, right? One of them is the ice forming process, which generally can also cause the typical rain that you see depending on the temperature of that day, or will cause a snowfall depending again on the temperature of that day. Okay, this precipitation, about 77% of the precipitation goes directly back to the ocean, so rains on top of the ocean essentially, and the other 7% that accounts for the total 84% comes from the precipitation that goes onto the land and then goes back to the ocean in the form of rivers and streams. Okay, so most of the water that is precipitated goes back to the ocean. So most, I mean about 77%, and that's like a direct going back to the ocean, and then the indirect way would be 7% from these rivers or runoffs. Okay, I do have a video that I want to just put it here before I move on, and the video is just a summary of this hydrologic cycle. Okay, continuing our class after the video. So let's talk about the fresh water. So fresh water is that water that we can consume, that's fit for human consumption. But again, not all of the water is available for human consumption. Most of the water that we get for human consumption, that is good for human consumption, comes from precipitation, from the water that precipitates, right? So in the evaporation process, most of the salt from that water from the oceans is left behind, and then when it precipitates, it can precipitate in different points on land, and then that's the water that we are going to access for our human needs. Okay, not all the water that precipitates goes back as fresh water. Okay, some of the water, like I said, is returned to the ocean, and some of the water that precipitates on land goes back to the atmosphere. So even the fresh water that is available, only portion of that fresh water we ended up actually and ends up staying on Earth's surface. Okay, let me put this in a more general way, because 2/3 of that water then goes back to the atmosphere. All right. The 1/3 that remains of that water, of that fresh water, that does not return to the atmosphere through the water cycle, um, exists in the form of runoffs that will follow downhills, or groundwater that will be absorbed into the surface. So here you have a very simple scheme showing the runoffs. The runoffs is that water that moves downhill across the surface of that land, okay, and that water came from precipitation. That water then eventually finds a stream, which is a moving body of water on land. So we can say that a stream is a running water. There isn't actually a big distinction between streams and runoffs. It's just more that the runoffs feed the streams, okay, and the streams will feed a lake or another river, and then from that stream you go send that water back into the ocean. Okay, so the runoffs, we can think of those waters coming from the mountains, for instance. But if you are on a hike in one of these mountains in this region, and then you happen to see a body of water that's running, the way you can tell whether that is a stream or not is how it's where that water is going to. Okay, so if that water is going back into the earth and then going and then appearing up again, then that's probably a stream. Okay, but the water that you see, that's very common. For instance, if you go on a hike right after it snows, right, you see that water sort of finding another little stream, another little river. That's a runoff. Then we also have the groundwater. The groundwater is the water that soaks into the ground, and then that water to go into the ground have to move through sediments, and we're going to talk about the groundwater as well in my next slide. Okay, this distribution between the runoff and the groundwater will depend on the type of the soil, the type of the dryness, and also the type of sediment that makes that soil. Okay, also the type of vegetation, the slope of that hill, and also how much the precipitation occurs in that region. Okay, I do have one slide I want to share with you, but I don't think it's in your PDF, but I just thought it would be interesting to show. Let me see if I can pull it up right there. Okay, so in the US we have these, and I'm sure also in other countries, but in the US we have these watersheds. So the watersheds, as you can see here, we have three main ones. They are large areas that are drained by streams that will end up in a river. Okay, so all the water in the area will be drained into a common river. So here I am showing you three of those big watersheds, and then we have the Columbia watershed, the Colorado watershed, and the Mississippi watershed. So that means that the water in this region will be drained all the way back, for instance, into the Mississippi River, or then in the Colorado River, or then in the Columbia River. Those waters from those rivers, they will then drain to another body of water. For instance, the water from Columbia and Colorado River, they will follow into the Pacific Ocean, right? And then from the Mississippi River goes into the Gulf of Mexico, which is located right there in this map. Okay, some of that water can also be groundwater. Some of that fresh water can be groundwater, okay? The groundwater can be simply defined as the water that goes underground, and that water invades the spaces between the sediments. Those sediments will be rocks or other soil particles, and they will infiltrate into those open spaces. Okay, this groundwater is really important because this groundwater is the water that we eventually we use for human consumption. Okay, because it's the source of water for wells, and also keep the streams flowing during dry periods in specific regions. Okay, like I said, this water, it's the type of fresh water that percolates, which means that moves downward from the surface. The amount of groundwater that we have, it's about 25 times larger than any supply on of fresh water on surface. So we do have a lot of water that's underground that we use. Okay, and it's often found within 100 meters from the surface. That groundwater will percolate downward, so will move downward into the floor, but that flow will depend on the pore spaces. Okay, whether those sediments have very open pore spaces, or more closed pore spaces. Okay, so if you have sediments such as sand and gravel, and by sand and gravel I mean the size of those sediments. Okay, we talked about this when we discussed about the sedimentary rocks. When we have sediments such as sand and gravel, they usually have a higher porosity and a higher permeability, which means that the spaces between these sediments is bigger, so water can infiltrate better into these regions. And I just want to make a distinction here that porosity and permeability are two different things, just for the sake of this class. So porosity we define as the amount of pore space in a sample of sediment, and then permeability is the ability of the sediment to transmit the water. They are both related, meaning that if the porosity is greater, the permeability will also be higher in that region. Okay, so if the porosity of the sediment is higher, the permeability in that region will also be higher. That's what I meant. Okay, usually clay type of sediment has a low porosity and low permeability therefore, and that's just because the sediments here, like you remember from our week number 5, the sediments of clay, they are usually smaller, so there is very little to no space for the water to move through these open spaces. Okay, that groundwater forms deposits. So here you're looking at those deposits. So the groundwater will move downward, and then that movement can come from a lake, from a river, or from a swamp that will infiltrate the soil underneath it. All right, so until it reaches a layer that is impermeable. That layer that is impermeable because the pressure of the material on top of that layer is so great that it compresses all the pore spaces here, that the water can no longer infiltrate that soil. Okay, so in this the zone between this this impermeable layer and the layer where the water is infiltrating is known as the zone of saturation. So you've got to think that the groundwater is moving down into the soil until it reaches this impermeable layer, and then when it reaches this impermeable layer, forms that zone of saturation. So the zone of saturation is that water, that groundwater collected just above the impermeable layer. okay? We also have here another type of layer that's called a water table, which is the boundary between the zone of saturation and the topmost boundary between those sediments, those materials. Here the water will eventually form this body of water that we call aquifer. The aquifer is just a place that holds a really big amount of water that can be used for human consumption. We say that, I know I'm calling here producing water, but we can think of an aquifer as that place that will hold water in usable quantity, in a quantity that we can use, essentially. Okay. And here that aquifer will form between two layers of impermeable water. When we have this aquifer forming between two layers of impermeable water, we have an artesian aquifer, meaning that to access that water, we've got to construct wells, okay, to access that water and make that water flow back into the surface. Some of those aquifers, they have areas of recharge, meaning that that area is an area that's directly connected to the aquifer and feeds the water back into the aquifer. I used to live in a place in Brazil where the zone that I lived had I think they had a specific name for that area, but it's like a nursing zone of the aquifer Guarani, which is one of the big deposits of groundwater in South America. If you know about South America, you might have heard about the aquifer Guarani. Guarani is a word that comes from the native Brazilians in that region. So that the area had a lot of laws in terms of being used or not, just because, again, it's a very protected area because the area of recharge feeds the water back into the aquifer, and then we use that water for human consumption. However, as you can imagine, money buys everything, and around the area they started building apartment complexes. And then what happened? As you can imagine, if you have more people in one area, what happens to that water? Drains. So capitalism was good enough in the area that they literally drained the whole area of recharge that my neighborhood was. I'm not really sure how the laws are right now, but I literally saw that happening. This beautiful area of recharge being drained all the way to its dryness, most dry point. Okay, so we do need I would say more stronger laws to protect those areas, because we're gonna use this water and we've got to protect where that water is coming from. Okay, so just some basic data for you to know. An average person, and here I'm talking about an average person in the US, because of course that would change according to your culture and places where you live, but an average person in the US uses about 470 liters of water, fresh water, per day. Okay, that is about almost 200 gallons, probably. I think it's like 170 something. That water is used mostly for agriculture, production of electricity, and a little bit for industrial, to produce clothing, to in slaughterhouses, to kill the cattle that you use to eat, and all of that other stuff. So we use lots of waters, but again, depending on the region, the usage can be different. Okay, I know that in your book there is a table that sort of breaks down how much you use in your household of that water, how much percentage you're using for for flushing the toilet or cooking or doing other activities. But just a general thing that I want you guys to observe here, when people talk about, oh, we've got to conserve water, right? Because we're using a lot of water. That is, true. We do have to be mindful of the amount of water we're using for the processes in our daily lives, especially in our houses, which means, the amount of time you're spending taking a shower, or how many, laundries you're doing on a week. But most of that water is also being used by agriculture. So we are villains, but we're not the biggest villain here in this story, okay? And that is not to say that we don't need the agriculture, because that's what puts food in our table, but we do have to be mindful about how we are producing those crops, okay? Most of this water that we use is coming from water in the surface, but also some water that is underground, some of the groundwater, essentially, okay? A little bit over 40% comes from the groundwater, which is a fresher type of water. It's a fresher type because it doesn't have as many sediments, bacteria, and pollution. So if you think that the sediments they can actually work as a filter, right? That holds smaller particles as the water is moving through. So waters in the aquifer are really, good for human consumption, just because they were sort of like naturally filtered by those sediments. The water on the surface is usually have to go through process to remove pollution. So that's why protecting those aquifers is really important, because doing the process of removing pollution from the water can be very expensive, as you might know. All right, some of that water, the liquid water, can also be found as seawater, right? Like I said, Earth is largely covered by water, and 7% of the Earth is covered by seawater specifically, okay? Most of that seawater is found in the oceans. The essential difference between ocean and seawater is that an ocean is a very large body of salty water, but if you're closer to the continent, then those waters can have a distinct characteristic that we're going to call them seas. So seas, the water closer to the continent that receives or that has specific characteristics of that region, and the ocean is that larger body of water, okay? Most of the ocean, as you can imagine, is still unexplored, just because there's a lot of water out there. We have three main oceans on Earth, right? We have the Pacific Ocean, which is the largest ocean that we have, with the greatest depth as well. We also have the Atlantic Ocean. There is something in the middle of this Atlantic Ocean that we talked, I think, in week number 5. What's the name of this thing that's in the Atlantic Ocean again? I happen to forget those things. Hopefully you still remember the name of the mid something that is found in the middle of the Atlantic Ocean. And then we have the Indian Ocean, which is the smallest ocean on Earth. Okay, like I said, here you have the simple definition of the ocean and the sea. So the ocean is just a continuous body of salt water that covers the Earth's surface, but the sea is that small region that's closer to the continent and has specific features of that region, such as the Mediterranean Sea, or the Gulf of Mexico, or the Caribbean Seas, okay? So in specific regions, that body of water receives a different name. The seawater, as you can imagine, has a lot of salt, but the salts here present in the seawater, they are different. So seawater has mainly chloride and sodium that makes up for sodium chloride, which is the table salt that we use for consumption. But we also have other chemical components in that water, such as bicarbonate. Remember that the oceans are a big reservoir of CO2, and that's because the CO2 is dissolved into bicarbonate. Okay, so CO2 combines with water, forms the carbonic acid, which quickly dissolves into bicarbonate and hydrogen ions. Okay, there are other things that also make up for that seawater, such as magnesium and calcium, which are other type of minerals that we can find in that seawater. All right, seawater is defined by their salinity. As you can imagine, there are some seawaters that are more salty or saltier than others, and that means that they have a higher salinity than other areas. So salinity is actually the amount of salt that is dissolved in that seawater. We say that is the amount of salt dissolved in 100 grams of seawater. Okay, the density of the water is about 1 grams per cubic centimeter, so 1 gram per ml. So here you would expect, for instance, that salinity is a percentage of the salt in that whole gram of water. Okay, most of the sea salt is about 35% salt, so that means that 30 grams of 1,000 grams of water, 35 grams of 1,000 grams of water would be salt. Okay, but there are other areas where this percentage can be higher or lower, such as the Mediterranean Sea, right? So this is an area where the salinity is really, really high. And that's just because of the currents that bring water out and in back to the Mediterranean Sea. Okay, water can also contain other substances, such as dissolved gases like the CO2 that will be found mainly in its format as bicarbonate. Okay, the seawater is always moving, and that movement forms currents or waves. So the movement of the seawater can be categorized into two types of motions, which can be currents and waves. Waves, they are small disturbances that will occur in the surface of the water, and that disturbance is usually caused by winds. Okay, that's the main cause of the waves. And currents are also another type of movement, but they involve moving the water from one location to the other. Okay, a wave is also moving the water, but in a smaller scale than a current. All right, it is estimated that the currents that exist on Earth mix the water on Earth every 2,000 years, essentially. So over the 3 billion years that Earth has existed for about 4.5 billion years, but it is estimated that this water has been mixed and mixed. I was gonna say recycled, but no, mixed on about 1.5 million times already. So every 2,000 years you have this water mixing completely. So the very first movement are the waves. And the waves are just like the waves we studied before. The waves in the water is just like the waves that we studied. Was that chapter through like week number 3 or 4? Week number 3 probably, right? So those waves, the water waves, also have a crest, also have a throw, also have a wave height, and a wave length. Because this is a normal wave. We can also calculate the wave period and the wave frequency, okay? Just like a sound wave or any other type of waves that we already studied. The wave height is the vertical distance between the throw and the crest. The crest is the highest point of that wave, and the throw is the deepest point of that wave. The wavelength is the distance between two crests, okay? And the period is how long that crest takes to move from one crest to the other, essentially, is the time between the passage of two consecutive crests. And we already studied this as well, all right? So waves can simply be defined as ripples that move across the water surface. So, the ocean waves, they are these moving disturbances that travels across the surface of the ocean. But if they are moving longer distance in a longer scale, then that is called a current. And what's causing the movement of the current is differences in density, differences in salinity, which influences density, differences in temperature as well. All right? Okay, so waves, again, the major factor that will cause the waves is the wind. What will determine how high that wave will be, how strong that wave will be, depends on the wind speed, also the length of time the wind blows, so how much time the wind is blowing in that region. As you can imagine, if there is no wind, there is no wave, the water is stationed. And the fetch, which is the distance that the wind blows across the open ocean. So for instance, smaller waves, you can imagine, larger waves, you can imagine that will be produced by stronger winds that blow for a longer time, and also fetch over and also blow over a longer fetch, okay, a longer distance. So those essentially produce a more larger wave. A wave that we're talking here is not a tsunami, that those are produced by events happening at the ocean floor, especially the movement of the plate tectonics. Okay, so when that wave hits the shore, some things can be observed, and they are, for instance, the refraction. So the refraction is when the water starts getting closer to the shore. So the water crest, the wave crest, starts getting closer to that shore. And as it gets closer to the shore, those waves, they become a little bit more slow. So they get slower and slower as they get closer to the shore, and that event we call refraction, okay? Usually that refraction happens because the refraction does happen because the wave front, or that the water crest, bends towards the shore, and they become more parallel to the shore. That's the wave that you see, okay? So the refraction is that very tip of the wave sort of leaning towards the shore, okay? We also have the breakers. So the breakers is, we can imagine as the wave gets closer to the shore, the wave front, which, it's the first part of the wave that will hit the shore, those wave fronts, they get steeper and steeper, so higher and higher, and the top of that wave starts overrunning the bottom part, so the top moves a little bit faster than the bottom part, which eventually leads to that top breaking forward, okay? And when that happens, that type of wave is called breaker. So before the wave breaks, we're going to call that event a refraction, when the wave is moving closer to the shore, and then that top part of the wave starts bending towards, as you can see here, the crest is bending towards. But at the point where that top part essentially overtakes the bottom, overruns the bottom, and sorts of breaks, we're going to call that a breaker. The zone in the ocean, the zone in the sea where that happens is known as the breaker zone or the surf zone. Okay, that's where people usually surf. That's why they are called the surf zone. And that this event of surfing is just because what we call surf in physical terms is the breaker formation zone. Okay, and that's what you see where usually surfaces they sort of are positioned on the wave. It's at that very point where the top of the wave starts bending and breaking. Okay, so surf is where the break of the waves will occur. And as the wave keeps moving, the wave keeps moving towards the shore by these breakers, but they must return at some point, right? So that the wave has this tide effect. The tide effect means it goes back and forth essentially. So that returning movement can cause the undertow and longshore currents. The undertow is this direct return of the water under the breaks. So below the breaks, the water is moving back. So this movement of going back is called undertow. You probably have felt that. I mean, if you've been to the sea before, to a beach before, and was in the sea, you probably felt that water underneath right below the waves sort of pushing you back. So that's what we call the undertow. And then we also have the longshore currents. The longshore currents, they occur because sometimes the water can be pushed sort of alongside, sort of like parallel to the shore or alongside the waves, and produce these longshore currents. Okay, so as you can these longshore currents, I think this is better represented here, is when this water will move parallel to the shore. So you have the shore here, and that water moves parallel. When you have two of those longshores finding each other, they will produce this rip current, and you can see this rip current in the picture. Right there is a rip current. I believe this one is also a rip current. Here we also have another one, and here we have another one, which is when you have this channeling of the longshore currents, because usually this part of the sea is a little bit deeper, which produces these rip tides when the longshore currents, they enter this channel, which we can define as a deeper projection, a deeper region adjacent to these regions. So this area here is deeper than this, and this one as well. Because of that, the water sorts of sinks back to the ocean. Okay, sinks and then moves back into the ocean. The rip currents can be really strong, and then in some beaches you will see some warning signs saying, oh, be careful with the rip currents in this area. Okay, because if you are pulled by one of these, it can be really hard to get out of. We also have the ocean current. So we just talked about the waves, which is one type of water motion. We also have the ocean currents, which is when large bodies of water will move, and they will move through long distance. Okay, they usually will move through the same path over and over, and those currents can be produced by two main factors: the density and the density differences in the sea water. This density will be mainly determined by, like I said, the temperature of the water and the salinity and the presence of sediments. So for instance, we know that cold water is denser than warmer water. So sort of the cold water pushes the warm water. So and that's the same effect that we had with the air masses when you have the cold air mass sort of pushing forward the hotter air mass. Okay, so this happens, the same thing happens with the water. So the cold water is denser, so it sinks underneath the hot water, pushing the hot water forward. And then we also have winds blowing in the same direction, and those winds are caused by those big convective cells that we studied before. So here I have one example of that density causing a current. So you have the cold and dense water from the Arctic region sort of pushing the water downwards. And I think here is very clear in this map that it pushes downward, but of course you have other currents here as well, just because the temperatures here is different, the salinity here is different in these regions, and that will influence how those currents will be moved. Like I said, three things can influence the density of those currents, of those ocean currents. That would be the temperature. For instance, cold waters are denser than hot waters. Okay, so the water in tropics usually is warmer and less dense than the waters from the polar regions. So polar regions will usually push the waters into the tropic, and that's what's represented in this picture. Salinity is also another factor. So the higher the salinity, as you can imagine, higher the density it is of that water. So higher the salinity, higher the density. That's what I meant. And the higher the density, the more it will displace the less dense water. So higher the salinity, easily or easier it will displace that water. And that happens here in the Mediterranean region, okay, in the Mediterranean Sea. So that water pushes the water in the adjacent region, sort of creating this north equatorial current that you observe here. Okay, and that's because of the differences between the salinity of this region and this region right next to it. Okay, another thing that influences the density of these currents is the amount of sediments, and the amount of sediments will produce these turbidity currents. The turbidity currents are the major mechanisms that move the sediments in the water, okay, in the ocean in general. So here we've got a map. Of course, I don't expect you guys to know the direction of every single current in this map. It's just to know that they exist, and depending on the region, they will have a different name, okay? So surface currents is essentially how the water moves through the globe. But again, the way this water will move will depend on the density, which we already talked. But the way the water moves will also depend on the shape of the ocean floor. I think I put this here on the ocean basin shape, but also on the rotation of Earth. And that's what we call the Coriolis effect, right? So the Coriolis effect determines that the water in the northern hemisphere will rotate to the right. And as you can see here, the currents are sort of going to the right, okay, in a clockwise movement, clockwise direction. And then in the southern hemisphere, those currents will rotate into to the left, or in a counterclockwise direction, as you can see here in the Brazil current or in the Peru current. Okay, they are moving counterclockwise. All right. those will form what we call the gyrus. So the gyrus are the great systems of water circulations, and they are found especially in the mid latitudes. So you have the equatorial current, you also have the polar currents on the poles. So those are going to be the major gyrus that are defined by how these waters are moving. Okay, and again, that will be determined by this Coriolis effect. The ocean floor has specific features, and I promise this is my last slide. All right, so the ocean floor has a continental shelf, a continental slope, and an ocean basin. A continental shelf is the margin, is where the water meets the continent. Continental shelf is not actually part of the ocean, it's part of the continent. Okay, it's this zone with the shallow water floated with seawater. It's essentially what forms the beaches. The distance, the wideness of this continental shelf is up to 70 kilometers away from the shore. Okay, and that shore was formed especially because the currents eroded the material from the continental margins. So this is a relatively shallow water compared to the basins, for instance. Then the transition between a continental shelf and the ocean basin is the continental slope. Slope means there is a decay, literally, so it's a steeper transition feature between the shelf and the ocean basin. Most of these continental slopes, they are 20 to 40 kilometers wide. And again, they are found between the continent and the deep ocean basin. Okay, they are often cut by submarine canyons. So we can think of those canyons similar, or at least similar, if not bigger, than the Grand Canyon that we have in Arizona region. And they were formed mainly by the erosions of the soil of that region caused by the turbidity currents and by the movement of the plates tectonics as well. Then the last portion of the ocean floor would be the ocean basin. The ocean basin is literally the bottom of the ocean floor, okay, which is the deepest part of the ocean floor. The ocean basin is characterized by the abyssal plain. The abyssal plain is the actual floor of the ocean, is literally the plain floor of the ocean. We also have some ridges. Those ridges are the mountain chain. What do we have here again? Well, I guess I have the name now. So those ridges are essentially mountain chains that are found in the ocean. And I think here I have a ridge, a representation of the ridge. So here's the Mid-Atlantic Ridge represented. It's not calling Atlantic just because you can't know whether it's in the Atlantic region or not, but that's why you see the mid-oceanic ridge. Remember that when we talked about the tectonic plates, we also mentioned that those ridges will have rifts, which is this through that exists between these mountains in the ocean. Okay, we also have sea mountains, which would be smaller than ridges. And another feature of this ocean basin is the presence of trenches. They are usually found right between the transition of the slope and the ocean basin, as you can see in this figure. Okay, so this figure is just representing the presence of the continental shelf. Then you have the slope, and then you have the ocean basin. Okay, which will have the abyssal plain, which is literally the ocean floor, and the ridges or even the trenches as well. In this map that you are looking here below, we have represented the ridges, Okay, the most famous one that I talked already about was the Mid-Atlantic Ridge. And then we have the trenches also represented here. We have the Peru-Chile Trench. We have other trenches around the U.S. territory, right? So trenches would be very low, deep parts of the ocean, okay? We also have volcanic peaks, and some of those volcanic peaks can form volcanic islands, such as the Hawaiian Islands, all right? And like I said, this is not a difficult class at all. I, only expect you guys to understand about, the hydrologic cycle, which we talked not only in this class, but in the class prior to this one. The water is always moving, and then we call that ocean currents and waves. We also talked about, the water present on the surface, the water that comes from precipitation. It's either stationed on that surface or then it goes back into the ground. Factors affecting that groundwater moving into the ground would be the porosity of the material and also the permeability of the material. We talked about ocean and sea. They are essentially the same thing. The difference is that the sea is that closer part of the ocean to the continent, okay, to the land, and because it's closer to the land, it will have specific characteristics of that region. We talked about the movement of this water in the ocean being influenced by the density of that water, and the density can be influenced by other factors. Earth rotation also influences the movement of that water, and the presence of the winds also influence the movement of that water. In that sense, we talked about ocean waves and also ocean currents. Okay, ocean waves and currents are types of disturbances and movements that happens with the water in the ocean. And then towards the end, we just talked about the ocean floor and its features, such as the continental shelf, continental slope, and the ocean basin, which is has the ridges, the abyssal plain, and trenches as well. Very easy, straightforward class, not hard. And last chapter, we're good to go. I guess now you guys know everything about Earth, or a little bit more about what exists on Earth, okay? Hope you guys enjoyed the whole course. I really enjoyed talking about not only the Earth, but the physical principles that govern the Earth. And it was a really fun course. Very long, but really, really, really fun studying about the Earth and revisiting some of the classes I took when I was your age, essentially. All right, good luck reviewing this class. Bye-bye.